Hello and welcome back to Statistics 1. We are starting Chapter 7. This lecture is on sampling error and sampling distributions. We already talked about the difference between the population and sample. We already made sure that the formulas for sample calculations and population calculations are not on the same pile. They use different variables. For instance, number of elements of a set for population would be capital N. The number of elements in a sample, right, or observations or data points would be labeled as lowercase n. Then we have standard deviation. One is sigma, one is s, and so on. So we distinguished between sample and population by understanding that population is all or everything you have. So if you say United States population, you mean every American citizen. It doesn't matter if the person was born here or naturalized. If the person has the certificate of citizenship and the passport and all that stuff, right, then that person is an American, which means belongs to population. Now, you can go anywhere, like you guys are a sample of American population here because you are not all American citizens, you are some of American citizens. We also talked about the ways to pick your samples, right? And today we're going to take a look into sampling distributions. We're going to take a look at the population and then see what are all of the possible samples that we can make. And we will show eventually that the mean and the standard deviation of the actual population data can be very well predicted or be the same as the mean and standard deviation of the sampling distribution. So we'll get there. First, we're just going to define the sampling error is the error resulting from using a sample to estimate a population characteristic. So sampling error is the error resulting from using a sample to estimate a population characteristic. So let's agree that we can, well, in theory, let's agree that we can find every single male American, right? So an American citizen who has a passport, certificate of membership, whatever, whether it's naturalized or born, doesn't matter. And we can get, let's say, all males, we can also do female, doesn't matter, and take their mean height. And the mean height is going to be a number. And then I come to this classroom where I have a whole bunch of samples sitting around, right? And I random pick 2, let's say. And then I measure their heights and then I average those heights. Would those 2 heights portray well the entire population? And the answer is no, right? Because entire population is going to have about 170 million people in it. And I just used the sample of 2 to predict what the value would be. Now, how about if I go to every single town in the United States and I pick 2 at random? That would be much better already, right? There are a lot of towns in the United States, right? And if you pick 2 from each, you are going to have a very sizable sample that would actually, on average, have a good prediction. Is it going to be exactly the same? No. Is it going to be good enough? Most likely, right? That's what they do for election, right? They go and they find many different ways in which they can survey people. Let's say, who do you want to vote for? They stop people on the street, they send letters, they send emails, they do phone calls. So all different types of survey are done in all regions. So you don't go to a particular neighborhood and just walk through, door to door, 10, 12 houses, and you say, yep, we're good. We know who wins the election, right? So the more you survey, the better. Now, again, there is the balance of how much you're surveying and how much, how accurate do you want to be. Clearly, if you survey the population, but that's what elections are, right? Everyone is allowed to go in and cast their vote. So sampling error is going to be an error that results from you trying to guess, right? Trying to guess something about the whole, which is the population, by looking at the sample, which is the part of population, right? So now, we're going to, so this is the first definition, and now we have the second definition. Let's go purple, I guess. And this one is sampling distribution of the sample mean. For a variable x, and a given sample size, the distribution of the variable x bar is called the sampling distribution of the sample mean. I'm going to underline sampling distribution. All right. And I'm going to also underline X bar. For those of you who do not remember, what was X bar? Mean of the sample. So summation of all xi values divided by lowercase n because it's a sample. And this was the formula to calculate. So this is from chapter 3. Now we're in 7.1. So calculates sample mean. Now they have done a problem in the book as an example, but I'm going to go into homework and work one of those exercises so you have, one that you read in the book and then you have one that I have done in addition, because there's only one example in the book and then they move on. That's it. I mean, one example done twice with the modification. This data is America's richest from Forbes as of September 16, 2013. So this is really old data, right? Right now, 6 years old. There's a lot of fluctuation with these numbers. So 717, that's the problem. And we have data. This is person, the name, and then wealth in billions. Now you can see that this is ancient because Bill Gates is on the top, right? Bill Gates is a kid now compared to Amazon, right? Bezos has his own private space program and pretty much anything else. So, but Gates was on top in this case with 72 billion, which is exactly about a half of what Bezos has right now. So that's what I said. This is really old. Warren Buffett, right? We'll go with the B on that one with the 59 billion. Larry Ellison, E, with 41 billion. Charles Kong is the C, that's going to be 36, followed by another 36 for David Koch, so that's D. And then Christy Wilton, W, is 35 billion. There we go. So this is the data. So they want us to calculate few things. First off, this is presented as a population because they are looking at the top 6 richest, right? If you're looking for the top 6 richest, well, this is all of them, right? This is the entire list of top 6 richest. So this is a population data. Are there more rich people out there? Of course, right? But they didn't make a list of top 6, which makes this into a population in respect to the restriction of top 6. Okay, so now we understand why is this labeled as population. Clearly, these are not the only 6 individuals alive on a planet. These are not 6 individuals that live in the United States, right? Only 6 individuals, right? There's everyone else, right? 350 million. So why are these labeled as population? Just because they populate the top 6, and there is no one else that fits the top 6 list other than these names. So now, since their population, for part A, we get to find the mean. Clearly, we have to look for mu, right? Because population mean is mu. You get to add all of these numbers and divide by 6.
46.5.
So 279 divided by 6, and you said that the average is?
46.5.
46, yes, we are only allowed to list one decimal place because our data had no decimal places. You are only allowed to give a single decimal place on that one. For sample size 2, construct the table similar to table on page 310. Okay, so part B, and this is what we are learning now. Please pay attention. They want us to create the table of all samples of size 2. All samples of size 2. So that's going to be Gates paired to each one of the other ones, right? Then you go with the Warren Buffett, right? Paired with every other one, and you go down the list. So that's going to be a lot of pairs. Create a table of all sample size 2 possibilities. And their X bars. All right, so what do I have? This is going to be a very long chart. I have GB, G comma B, G comma E, G comma C, G comma D, and G comma W. So these are all samples that involve Bill Gates, because this is Bill Gates pairing up with every single other possibility out there. So this is, right, this is sample, and this will be their X bars. So we have Bill Gates pairing up with every single other. Then we are going to go with Warren Buffett with B. Now, we're not going to go with Bill Gates now, because we already have Buffett and Gates right there, right? So we're just going to go down the list. So BE, BC, BD, and BW. Sample size 2 continuous. Maybe I can do it on the side. Sample X bar. Then we are moving to Larry Ellison, and that's going to be E combined with C, E combined with D, and E combined with W. All other combinations are already part. Here's the E right there, is the E right there. So, right, you have all of those interactions already there. Okay, the next one is C, so it's going to be CD, CW. Then we have DW, and we're done. So these are all of the samples that you can come up with size 2. There are no more than this. Right? This is it. So the fastest way to come up with this is to use that system, right? You pin the first one, like we pinned Bill Gates, and then, go with the Bill Gates name along every single other name from the list. And then when you're done with that, move to the next, rinse and repeat throughout the entire process. So now your job is to find X bars for every single one of these, right? So it takes a long time, but 72 plus 59, that's 131. So the first one is 131 divided by 2. That's what? 65.5. So $65.5 billion if I average Bill Gates and Warren Buffett, right? Then we have Bill Gates and Larry. So that's going to be 113 divided by 2. 113 divided by 2. 56.5. And then we have a GC. So Gates of 72 and 36,108. So that's 54. GD is the same, 54. And then 35 is just going to be 53.5 because it's one less. You're dividing by 2. Now BE, 59 and 41, that's 100 divided by 2 is exactly 50 for BE. BC, 59 plus 36, that's 80, 90, 95, right? I'm sorry? 47.5. And the next one is 47.5. And finally, we have a BW. So that's going to be 30, 80, 84. No, 94, right? 94. So 94 divided by 2 is 47. No.
Yeah. Is that right? 47.
So 47. Now we go with E and C. That's going to be 41 plus 36. That's 77. Half of 77. 38.5. And then the next one is the same, right? 38.5. And now we have the last one. So that's going to be 41 plus 35. That's 78. No. 76. 76 divided by 2. 30. Yes. CD, so that's going to be, well, they're just averaging 36 both, so that's easy. 36 plus 35, that's going to be 35.5 because that's the number that's in the middle. And finally, DW, also 35.5. Mathematical magic. Without calculating, if I am to find the mean of these means, mean of means, the answer will be 46.5. I know, right? Am I amazing or what? Let's go. Let's add all of these numbers. See what we get. What happened?
I'm missing one somewhere in my chart. Because I didn't want to look at it.
You found yours?
Yeah.
What years is that? EW?
What is going on here? Like, is anyone like? Okay, so let me backtrack because no one is asking any questions, and I know you got 46.5. Beautiful. So if you are, so let me just say, mean of all x bars is going to be 46.5. And how do I know? It's 46.5 right there. So these two numbers have to be the same. Now, let's backpedal and see why, right? If you have population of 6 and you just found the mean, why? Well, we are actually setting ourselves up for some future lessons where you are not going to know anything about population. Chapter 7, and this lecture in particular, is just there to show that there is equivalence from what you calculate in population if you know it, and then when you look at the samples and what you get from samples. Now, why I think that this is an amazing exercise, even though it's very labor intensive and completely pointless, right? Because you would never, right, in a right mind, do this if you have 6 numbers to average to begin with, right? Why would you go through all of this to get the same value at the end, right, with this master mean at the end? Well, that's not the point of this exercise. The point of this exercise is to show that if you have some kind of population, and if you want to think about all male or all female in US and their average height, right? Remember what I said. I'm going to pick 2 from this classroom, right? And I'm just going to average their height and then make the inference about the whole United States. That's terrible, right? Now look how terrible is this, right? This is really terrible. Because when you take a look at the average of the top 2 on 65.5, and the average of all is actually 46.5, guys, that's 20 billion off. 20 billion. That's a lot of cat food, right? So we see that not every sample that you pick is good, right? Do we have a 46.5? Exactly. We don't have 46.5. We have 47.5. We have a 47. 47 is the closest, right? All right. That's only $500 million. It's not a big deal, right? So, but that's this one, right? This is why I don't bother with your exam average. Students immediately, right, when I walk in, what was the average of the test? Just think of this situation and understand that you alone, you're a sample of 1, right? Because you have your grade, whether it's 100 or 23. So if your grade is either 100 or 23 and the class average was 71, how's that class average in any aspect, right, describing your grade? It is not, right? Because if your grade is 23 or 43, doesn't matter, right? Or on the other end, let's say 100 or 98, like average of 71, right? It does nothing for you. Now, obviously, right, you get to, feel good if the average and you're above the average and so on, so you get to brag, you put on a fridge with a magnet, obviously, right? I understand all that stuff. Now, what we have done in this chart is we created all possible samples, and we just found means for each one of those samples. And when I found the mean for each one of those samples, I realized that the vast majority of these samples are terrible, because anytime I pick, pretty much anytime I pick, I'm always off, and I'm off by a lot from actually what the population mean is. That's 20 billion off. At best, I am $500 million off. That's $500 million, right? We get to do this problem again now, but now we're going to use samples of 3. And then we get to do this problem again with samples of 4. Now, clearly, this is the longest and the most annoying calculation because you have a lot of samples of 2. You are going to have less samples of 3 and then even less samples of 4. So those calculations will not be any, together they're going to be less annoying than this single one, right? So let's continue with this problem now and create the sample size 3. And I believe that's the next. No, it's not. No. What happened?
I'm done.
You're done. I understand. Now, start writing. Sample size 3. Okay. So if I have a sample size 3, sample, and then X bar. For sample size 3, I take the first 3. So that's Gates, Buffett, and Ellison, right? So GBE, GBC, GBD, and GBW. So we got the sample of 3, including gates. Right? Now, Gates is done. Right? Or no? Is Gates done? No, Gates is not done. Now we go GEC. Okay, so now GEC, GED, GEW. Wait, are we going to have more here? It's supposed to be less. And then GCD, 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 GCW, GCD, GCW. Oh, thank you. So GCD, GCW, and GDW. Okay, so those are all with Gates now, because Gates now paired with everyone. B. B is, this is, you know, this is the fun stuff. I mean, we can do calculus. I never actually had that before. I was like, really? Okay, I'll take calculus because this is tedious. Yes, which is why you need to focus. Now I lost where I was, so let's go with the next section, right? We'll just leave it here. You open the notes. What happened? We gave up. BEC, BED, BEW, BED, BEW. A holy nightmare. Okay, we're BEC, BD, BW, BCD, BCW, BCD, BCW. Yeah, this is going to be much worse, actually. I lied. And then BDW, and we're done with B's. Nice. I was looking at the clock. We just want the class to be over. Okay, ECD, ECW. We're done with these. ECD, ECW. Oh no, EDW. EDW, there we go. And the last one is CDW. Excellent. We have few. And now averages. Yeah, this is much longer. I did. It's perfect. Next one we're going to do with 15. We're going to sleep here.
We're boycotting.
You are boycotting, exactly. So what's 172 divided by 3? That's the first, GBE.
57.3.
57.3. Excellent.
55.6.
55.6.
55.3.
55.3.
55.3.
Again?
Mm-hmm.
Nice.
49.6.
49.6.
49.6.
Please tell me that you're not making this up.
49.3.
49 points. She has a calculator that does this for.
144.
How much?
144.
144?
Wait, hold on.
What's a GCD? Oh, 144.
48, 48.
Exactly 48?
Yes, and that's where I'm at.
Well, that's much more than I anticipated, so this is amazing. GCW, GCW, that's 72 plus 36 plus 30. That's the same number of 48, right? Because the same values are used.
No,
No?
That's 35.
it's 47.6.
47.6, okay. And I'll just put over here lots of numbers.
Yes.
Lots of numbers. It's the, yes, that was the sign. Lots of numbers. Now, what I need you, hold on guys, we still have 4 minutes. We can spend some quality time with these numbers. Now, what have you noticed when my sample size went from 2 to 3?
It increased.
These numbers increased, right? The error decreased. Remember that we started this lecture with a sampling error, and I said you pick a random sample, you take the mean of that sample, and you try to make a prediction about the population mean. And the sampling error is the error that it's actually, how much this thing is wrong. Observe the number on the first one. It was 65.5. It was 20 billion off. Look at this one, right? This one is 11 billion off. So now, all of the numbers that you are going to get for all of these sample 3, all of those numbers are much closer to the actual 46.5. Now, 46.5, probably we're going to get something very close to 46.5. Last time we had 47, so that was, right, $500 million off. We might get some of these to get close to 46 now, 46.5. So what are we learning here? We're learning here that the bigger the sample, less error. And that's why we had to go through these painful exercises so you can see it. If we are using sample size 2, on the first row up there with Gates, right, we made a $20 billion error. Now, with also Gates and Buffet, right, in a first, we have an error that it's 11 billion. That's much better than an error of 20 billion. Is 11 billion big error? Of course it is, right? But the trick is that what happens if I go to 4? It gets even better. If I go to 5, it gets even better. If I go to 6, well, that was my population, so it's going to be exact. Yes?
So it's getting better, but even if we took the mean of this one, it would still be 46.5.
Yes, if we are to compute these lots of numbers over here, and you take the mean of all of those means, it's going to land exactly at 46. So mean of means is going to be equal to population mean. Now the trick is that you never have a population mean, right? You don't go out there and measure every single guy, American, right? To acquire 350 million data points to say this is, it's not 350 million, half of that, to acquire all of those. Because by the time you collect the data, what happens? That's accidents, births, right? You just finished with one town, one city. Let's say you got them all the next day, right? Because we have 30,000 dying in car accidents alone. Just that, there's nothing else. 30,000 in United States alone. So you cannot, right, come up with this mean of all heights for male or female, doesn't matter. because it's just population, right, is too big. Maybe you can pull it in Norway, right? They have 5 million, right? So if you invest, someone like really crazy goes and throws the money at it, you could probably pull it off in Norway with 5 million population. But here on 350, there's no way, no way. So that's our first lesson, and we learned that the bigger the sample, the better the results, the more accurate the results. And the rest of the chapter 7 is going to expand on that and push it further. See you next week.